Welcome everyone, my name is Bach and I'm happy to welcome you to today's workshop on analyzing survey data with weights, a practical introduction by Stefan Zins. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research that provides a platform for early career researchers to present tools, methods for the collection, management, analysis and visualization of data in the social sciences. Our speaker today is Stefan Zins, who is a senior researcher in the Statistical Methods Department at the Institute for Employment Research, IAB, in Nuremberg, specializing in survey statistics. In his talk today, he will talk about basic insights into the construction and logic of survey weights and the appropriate methods for using them for statistical inference. Some logistics. We are recording this live stream in active speaker mode, which means audio from on-site and remote attendees will be recorded, and if your video is on while asking a question online, your video will be recorded as well. For those joining us online, you may ask your questions by raising your hand or posting your questions online to the Zoom chat, and I will read them out for you. All right, I'll hand over to you, Stefan.
Thank you very much, Ruben, for the kind introduction. So, yeah. Okay, as introduced to this topic, I will try to give a practical introduction to analyzing survey data with weights. For that, I have to introduce a little bit of theory, but I try to be brief there. So I give a brief introduction into the design-based framework for doing inference. Design-based meaning that we want to make inference about a finite population, so it's a finite set of elements from which a sample is drawn, and then we analyze that sample. Okay.
I click once onto the main screen.
Good. Now it works. Perfect. So the outline of my talk today, as I said, a short introduction. Then I will move on and talk a little bit about non-response, because non-response is one of the reasons why survey weights are being constructed, or what we want to address with survey weights. Then I'm talking very briefly about the R survey package, which is the software tool I'm using here in my examples. I hope at least some of you are familiar with R. You can do the exact same thing with data. That's also possible, but the examples are in R. Then I move on to some practical applications where I use some data from the European Social Survey Wave 8, and just an example when analyzing data from one particular country, which is Austria. Then another example showing how to do standard error or variance estimation under non-response. And there I'm trying to do the full set, where you start from the gross sample, which has some survey weights, some design weights associated with it, and then we resample that, and then we repeat the whole process of producing survey weights. Okay, and then I will conclude with some summary and final remarks. Okay, so introduction to the design-based framework. Just before we start, maybe some of you are aware with this framework of the total survey error, where we have these two columns. One is the measurement, one is the representation. We are only concerned today with the column on the right representation. So we have a target population, which is finite. Then we have a frame of that target population, which hopefully it enumerates all elements in the target population and only the elements in the target population. So that's where coverage error could come into play. Not talking about the promised coverage error today, but it is also something that you could address with weights. Then we select a sample from our sampling frame, and then we send this so-called gross sample into the field, and then a response happens. So usually if you want to survey persons or even establishments, not every unit will respond, and then we are left with a set of response, which is the only set for which we have observations and which we can then use to do inference. So when you see here this conceptual framework, the different steps where errors can occur in that process. Okay, just Now, coming to this brief introduction of the design-based framework, so what we have is a finite population of capital N elements. I'm representing here our variable of interest, y. It's just a variable which has a certain value for each element in the population. Then we have a set of auxiliary informations which we're going later to use to construct weights or to explain response propensities. And annotation, I annotate X. And then we have our sampling frame, which is U. So U is just enumeration of our finite population. And if this enumeration is complete and only includes and only elements from the target population, we don't have any coverage problems. And then our sample is simply a subset of that sampling frame. So that's it. So that's the sample. Can be selected in any way. So here, this framework would even work, for a probability sample, just defining the sample as a subset of the sampling frame. Okay, so the important thing is here in this design-based framework, we don't have any explicit distribution assumptions about the data. So basically, our whole population is described by this empirical data. We don't make any theoretical assumptions about distributions of data. So we don't assume that y follows some normal distribution or x follows some distribution. So the only thing random here in that framework is the selection of the sample, if you're selecting a random sample. So, and that brings us to this only random variable that we have, or one of the two response indicators, another one, but now is the sample indicator. So is a unit included into the sample or not? So this is I. So ik is 1 if the kth unit in the sampling frame is included into the sample, and 0 if it isn't. And the expected value, which I notate here with this E, is the inclusion probability. So that tells me what is the probability of k being selected in any of the possible samples. The set of possible samples is created by the sampling algorithm that you're using. So that not going into that technicality. So that's the first order inclusion probability. Then you can have inclusion probabilities of higher order. And one important one is the second order, or the joint inclusion probability, pi KL, which is the probability that unit K and L are included jointly into the sample, so that they are both together in the same sample. That is important for variance estimation later, which you'll see in the 2 slides. Okay, so why is this inclusion probability important? If we want to construct an unbiased estimator, and this is an example for an estimator of a total. And the total, or this estimate I'm showing is like the workhorse in design-based inference, not because it's such an important statistic to estimate totals, maybe means are more common, or averaging statistics, but many estimators can be expressed as functions of totals. So your mean is a function of 2 totals. The denominator totals, that's your mean. Also regression coefficients. In OLS regression, I can write that up as a function of totals. That's why it is important, or often you see in textbooks, they cover the variance of totals, because you can bring many estimation problems down to estimation function of totals, and then you can do standard error estimation as you would do for totals. Using the right tools, linearization and so on, if you have to deal with nonlinear statistics and so on. Okay, so coming back to this Herbert-Thompson estimator. So we want to estimate the total of our variable of interest y, which I defined here as tau. And based on our set, on our growth sample, so we don't have any non-response here. And I simply weight the observations in the growth samples by the inclusion probability. And if I write that down in matrix algebra, I have this vector d, which are the design weights transposed, multiplied by the vector of the observations from my sample. Or I have here the vector of the elements that are included into the sample, and then I have this vector which is the observations divided by the inclusion probabilities. The difference is that this vector here is on the length of the population, and that one does not, but both the same value. Okay. Why is this an unbiased estimator for the total? Okay, just down below, I want to have now I'm looking at the expected value of this estimator. So takes on the sum form here, and I put the expected value around this sum. And if you remember, the only random variable here in this whole framework is I. This is the sampling indicator. So I can put the expected value into this sum. These are constants. These are non-random numbers. The expected value is equal to the value, to the observed value. And the expected value of the sampling indicator is equal to the inclusion probability. So this cancels out, leaves us with the total for the whole population. So see that sum here runs over the whole sampling frame, and now here the sample indicator. And that's the trick how we often see how it's shown that the estimator is unbiased. In the design-based framework, you go over the sum of the whole sampling frame or the whole population, and you use the sample indicator here to signal what I only have the observations that are included in the sample. And that's basically that's why weighting by the inclusion probabilities here in the total brings you an unbiased estimator. Now, to the variance of that estimator, because it's also important, and I'm being generic here, so it doesn't get more complex at this slide. So, what is the variance of that estimator? And as I said, the sample indicator is the only random variable here. So, variance has a quadratic form, so I have this quadratic form here. So, from the left side and then from the right side, I have these vectors here for my variable of interest, where the values are divided by their respective inclusion probabilities of the elements. And in the middle, I have the covariance matrix of my sample indicator. Because that's the only random variable. And if I'm interested in the variance of that construct here, that's how that would look like. Okay, how do I estimate this? I divide that covariance matrix by the second order inclusion probabilities. So that's how the covariance looks like. Each element of the covariance matrix here in this delta has this form. You have the second order inclusion probabilities minus the product of the first order inclusion probabilities. How covariance looks like? Combined expected values minus the product of the single expected values. And then I'm dividing this by this joint inclusion probability. And then I have here my estimator for the variance of my Hertz-Thompson estimator. So this is the most generic form. And this will simplify very much if you're having simple sampling designs. If you're having a simple random sample, all these inclusion probabilities are constant. The first order inclusion probabilities for a simple random sample is small n sample size divided by capital N size of your sampling frame. And that here takes also a constant form. For every combination of K and L, this is a constant. This is small n times n minus 1 divided by capital N times capital N minus 1. So this is the joint inclusion probability for a simple random sampling without replacement. And then you can write this down, and then you can simplify this expression, and you come up with this, what we all seen, the variance for a simple random sample of a mean or a total in a textbook. This is equivalent, but this is just the generic form. So this is just to show the importance, of the distribution of this sample indicator. This is what drives the variance of your estimates in this design-based setting. Yeah. So as I said, even for more complex statistics, all boils down. Often you can reduce that to the problem of estimating the variance of a total or multiple totals. One alternative, which we will also see in an example, is resampling. This works obviously different. There, I resample my existing sample according to the mechanism, delete one jackknife, for instance, and deleting one unit at a time, and recomputing my statistic and adjusting the weights accordingly to this reduced sample set. Or I'm doing a bootstrap where I have a permutation of my observed sample and then recomputing the statistic for each permutation. And then I'm estimating the variance of over the replicates that I'm producing, or the variance of these replications. Okay, so that is the first application of weighting, simply to have unbiased estimation. So even in the absence of non-response, and you have perfect response, you might want to use weights to have an unbiased estimation. Because of course, in a simple random sample, you don't have weights in that sense that they are constants, and you can then use a simple estimator. But your sampling design doesn't necessarily need to have constant inclusion probabilities. Think, for instance, of sampling proportional to size. Or if you want to survey establishments you're interested in the number of or turnover in an industry. And then, a much more efficient design than simple random sampling would be maybe to sample the establishments if you have some information in your sampling frame associated with each unit about the number of employees that these establishments have, or the taxes that they have filed in the last year. Then you can sample proportional to that. And if that variable is related to what you would like to measure, and this is then a much more efficient estimator than doing a simple random sample. Especially if you have a market structure where you have many small establishments and a couple of big ones. Example, think of that. The car industry. Maybe you have many smaller workshops that make custom cars and so on, but you have huge big ones. And you would never then sample a simple random sample where you're missing, I don't know, Volkswagen in your sample. That would be stupid. So you would try to have a sampling design where the inclusion probability is related to what you would like to measure. And then you have unequal inclusion probabilities, and then from that your so-called design weights are then derived. Okay, but coming now to non-response, which is also a reason why to use weights. So this is just a representation. Non-response will be our sampling frame. Then we have our growth sample, and then only a subset of that growth sample responds. However, that happens. So, and that mechanism is usually modeled that every element in the growth sample or every element in the sampling frame has a certain probability of responding. And that probability of responding is independent of the probability of each other element in the frame of responding. So we have now this set of respondents, which is a subset of the growth sample. And then again, we have this random number, which is the response indicator. And it takes on the value of 1 if the element is part of the set of respondents and 0 otherwise. And then we have here the expected values, theta k, which is the response propensity of the kth element in the growth sample. And here, the product simply of the independent response propensities is the joint probability of two elements responding at the same time. So this is basically what you might know as Poisson sampling, where every element is assigned a certain inclusion probability, and you could implement Poisson sampling then by drawing a uniform random number, and if that random number is smaller than the assigned inclusion probability, you select that unit. If it's larger, you don't select it. And you do that for every element in the sampling frame. Then you have Poisson sampling. And that's how often response is being imagined. It is independent of, the response of one unit is independent of the response of other units. If that is really the case, sometimes probably not. Think of adaptive designs where maybe the field work shifts depending on how the response process happened before, and then certain units get higher attention, or maybe more incentives offered, and so on. So, but this is the basic framework. The difference is that theta is unknown. So we don't know what theta is. So we have to estimate it or somehow correct for that. So if I'm writing here up our estimator from some slides before, the Thompson estimator, we see that this is now no longer an unbiased estimator if I'm only weighing by the inclusion probabilities of the growth sample. But that would only be true if theta would be equal to 1, response propensity equal 1 for every element in the sampling frame. So it obviously is not the case in most applications. So we have to find some weights, which I here denote as WK. So that this sum, which runs only over the respondents, gives us again an unbiased estimator for our total. And one way, of course, to do that is to find WK, which is equal to that. So, but theta, as I said, is unknown, so we have to estimate it. So that is only for unbiased estimation. Non-response will always affect the variance of the estimator, even if that theta is a constant value. So everybody has a response propensity of 0.5. So this would not necessarily introduce any non-response bias in your mean estimate, for instance, constant, because it's independent of what you're measuring, your response. But still, this additional selection step will introduce additional variation in your estimation strategy. And it goes, of course, also if there is some dependencies. Just to illustrate that, if you hear somebody say, well, so it's kind of messy, I'm mostly interested in estimating models. So I'm interested in associations and causalities, let's say. So I'm not using weights. Okay, so this is just an example on showing how that could go wrong. So you see this point cloud here. This is the population. That's the growth sample. That's how your growth sample would look like. You have two variables, variable y, variable x, and you're interested in the association between them. And as you can see, there is none. But we have three different groups. And as you can already see, if I would, make a regression line within these groups, there would be some dependency. So if I would fit a regression line only to the black points, green points, and red points, there would be a negative association. Now, what happens if response is different in these three groups? This is just the R output for the regression on the growth sample. You see here, that's the somewhat around 0, and it's not significant. Okay, now non-response happens. And we have a disproportionate non-response in the green and in the red. And now the regression line takes on some slope. And this is the regression only fitted on the net sample. I don't use any weights, I'm just regressing on the net sample. And now I'm having a highly significant association between the two variables. So, of course, that's bad. If that happens. So now the blue line is if I'm using estimated response propensity. Of course, in that example, I created the non-response. I know, how it's being constructed, so then I can estimate it. And then you have this blue line, which is the weighted regression. I'm using here the survey package from R, survey GLM, and I computed non-response weights and then did this regression again. And now I'm not having here the same estimate for the coefficient as in a growth sample, but again, it's not significant, the association. But at least your test remains correct. Okay, that's just to illustrate that weights matter, because even if you're interested in associations, that doesn't mean you can define any selection process away. You still have to consider how the data has been constructed, or how you arrive at this net sample. Just a short excursion on the topic of non-probability samples. So non-probability samples, roughly defined, you have a sample and you don't really know the sampling design. Yeah, maybe you know how to describe a sampling algorithm. You know, you can somehow describe how this has been selected, but you don't have enough information to compute any inclusion probability. So, for all intents and purposes, it's a sample with unknown design. You know, you have some sample, but you don't know the sampling design, and you don't know any inclusion probabilities. So this problem then takes doing inference with a non-probability sample takes on a similar form as doing inference under non-response, where we then now have to estimate the inclusion probabilities, so not the response propensities, but the inclusion probabilities. And hopefully we have some auxiliary information with which we can do that. And again, this works relies on similar assumptions as with modeling response propensities. Inclusion is independent of each other. Here, every element has a positive probability of being included. And this problem here has the simple form where we say that S is actually a subset of our target population, which in some non-probability case doesn't need to be the case. I mean, you could have an overcoverage, which maybe is hard for you to identify because there is no clear defined sampling frame from which the non-probability sample has been selected. But most inferential problems are structured in a similar fashion with non-probability samples as it is on the estimation with non-response. Okay, so some weighting methods. We've already talked about response propensities, estimation response propensities. So I want to estimate this theta here. What do I need for that? I need auxiliary information on the level of the gross sample. I can only estimate that if I have auxiliary information for every unit in the gross sample, regardless of response. Think of some demographic information that is available in the sampling frame, if we are talking about persons, where they live, in which region, which age bracket they are, maybe their gender, maybe the education level, things like that. So that is available from some administrative data source, and I can then use that to construct a probability regression, logic regression, some model to model a binary variable, which is the response indicator. So what we hope to find is that we can have this relation here satisfied so that the response conditions on our auxiliary information is independent of our variable of interest. And this is also called this missing at random assumption, so that conditioned on some auxiliary information, response doesn't depend anymore on our variable of interest. And then we can use the estimated response propensities to do unbiased inference. So classic models of doing that is, as I said, generalized linear regression, but you can also use any other method that is suitable to model a binary outcome, which can include some other machine learning methods, random forest regression, and so on. Again, important is that the information is available on the level of the browser. Then calibration. Calibration is another well-known method of constructing servo weights. There, I'm having some input weights, which can either be our design weights, only for the elements in the net sample, or already a combination of design weights, and I should have put a hat on here, estimated response propensities. So how calibration works, so having some incoming weights, they can also be just ones, doesn't really matter for the method to work. But in practice, often you have some incoming weights as either the design, so-called design weights, so the inverse inclusion probabilities, or inclusion probabilities adjusted by response propensities. And then these weights are adjusted in such a way that they replicate some known population points. And that's what I'm writing here. So I'm having here again the set, my net sample set, and I'm looking for a vector of weights, or a set of weights, which satisfies this equation here. So the weights are then constructed that they will replicate known population statistics, like age, gender distribution, for instance, which you know from the population. there are different methods on how to solve this. Is basically your optimization problem under constraints. And yeah, to resolve this, then you have a vector, and if you then use that vector, to estimate the totals of these variables on which you calibrated on, they will exactly replicate these totals. The difference between just doing calibration weights to estimating non-response propensities, they maybe need a little bit less information or different information. For calibration, I only need the access on the set of the respondents and not on the whole growth sample. But I need population totals. So what it often is in practice, I'm having a survey measurement and I'm having some similar measurement from official statistics. Say I have education measured here, but I don't have in my sampling frame any information about education. But I know from some census data, education distribution by gender and so on. And I can use that information to calibrate on. So the population information could come from any source, doesn't need to be like the totals calculated from your sampling frame. That's what often done in practice. And the access only need to be observed for the survey. So that's my often, maybe you can employ more information or use more wider range of variables in your calibration as in your response propensity estimation, because information that is available in the sampling frame for each unit might be a little bit sparse. Okay, so what calibration does, if these axes also explain the response process, same as the response propensity estimation, they help to reduce response bias or eliminate it. On top of that, calibration can also reduce the sampling or the standard error of your estimates. If these axes are related to what you would like to measure, then they can actually help to reduce the standard error. So this is just to show that it does not need, what some people you might say, there is a trade-off between using weights and variance. So you're using weights to reduce bias, but it will increase your variance. So maybe that is a net zero game, with respect to the mean square error, but it does not need to be the case. So calibration weights can actually also reduce your standard errors. I'm going to show you that on the next slide, because this was also the original intent of these type of estimators, which is also called the generalized regression estimator, CRAG. Calibration estimator and grade estimator can be the same thing, depending on the method I'm using to solve this optimization problem, where I'm looking for the set of weights that fulfill these calibration requirements, that they replicate these totals. Okay, so what we have here, again, there's a point cloud. This is data from some sample, and the blue lines correspond to the design weighted estimates. So I'm having here the mean of my variable of interest and the mean of my auxiliary variable. And the red line is the regression through this point cloud. And the means, because of the properties of this regression, have to be on the point cloud. Okay, so the green line is now my calibration estimator or grade estimator. So what I'm doing here, I'm exploiting this relationship between the auxiliary information and my variable of interest. And mu x is the known population mean of this auxiliary information. I'm having that from some source of official statistics, let's say. So I'm basically plugging in here the mean into this regression, and then I'm adjusting my design-based estimator by this bit. So I'm using the relationship that's being estimated based on the sample data between auxiliary information and my variable of interest, and then I'm plugging in some known auxiliary information, the known means of the auxiliary information, to get to a new mean estimate of my variable of interest. And this is what calibration does, what a grade estimator does. And that's how it can help to reduce standard error in estimation. Okay, so this is just a graphical representation of the calibration estimator. Okay, so just going to the technical part, the R survey package. Just going over this quickly because that is what I used in the examples. There's the literature from Thomas Lumley, it's the main developer of that package, or at least he used to be. I'm using that version 4.4. It's from last year, so there is a newer one already available. Then there's the book. It's quite old. You see how long it has already been around. So this was the original book published as a textbook with that package. But there's some update here, and you can also visit the homepage. So what that survey package does, besides handling survey weights, is it also handles design-based estimation. So I'm defining my sampling design, including weights, if I want to. So there are some main variables to consider. ID is to specify the sampling units. Strata is to define certification, if there was any certification in the sampling design. Weights, if I want to use some explicit sampling weights in the estimation. Calibration formula is there to tell the package that the weights have already been calibrated. So there I'm defining on which variables or what's the calibration formula on which the weights have been calibrated to. Because then he can use the correct variance estimator for estimation of standard errors when I'm using calibration weights. And FPC, if available, is a finite population correction. So there I can tell how large have been the strata and how large have been the PSUs if there's been multi-stage sampling. So this package also covers multi-stage sampling, or if I'm sampling at the first stage PSUs, and then sampling SSUs, secondary sampling units within PSUs. I can tell the package how large have been the PSUs, so that this can also be considered in variance estimation. So now I'm jumping right into this application here with the ESS 8. I'm using data from Austria. This is just the information on the sampling design. It's a rather complex sampling design. So yeah, the sampling frame is a register of addresses households from the Austrian Postal Service. Then Austria has two sampling domains. One is Vienna, being by far the largest city in Austria. So Vienna is stratified, and then for whom these strata households are being selected. And then from the households, persons are being selected. And then for the rest of the countries, municipalities are selected according to a NUTS-3 stratification. And then, these Zählsprengel are selected at the first sampling stage. This is some statistical unit in Austria that serve as primary sampling units. And then from these so-called Zählsprengel, households are being selected, and then from within the households, persons are being selected, just one person per household. The ESS only provides information on the PSUs, so it doesn't go below that. But it's the only thing that we can use here in estimation. As you might know, the sampling design, of course, also affects the standard error estimation, and cluster sampling or multi-stage sampling can have a huge effect on your standard errors. But the ESS doesn't go down that much. It only provides information on the PSU membership of the elements in the sample. That can be fine. Only providing a PSU information covers already a large part of the variance, or can already cover a large part of the variance. And then adding information about secondary sampling units, or even at the third stage, maybe doesn't contribute that much to the standard error estimation. Okay. So ESS provides two types of weights. First are the design weights. This is also perfectly just the inclusion probabilities or inverse inclusion probabilities. Sorry, I put here the inverse here. So these are the inverse inclusion probabilities of the growth sample, and then so-called post-certification weights. I call them so-called because they're actually rating weights in most cases. So Here, post-stratification is simply a one-stage adjustment, and rating is a little bit more complex. So post-stratification works. You have the first classification of all your weighting variables. Usually, category data is being used, like age, gender, and education, and then the weights are being adjusted so that these known population tables are being replicated. In raking, that's an iterative procedure where you don't have the full crossing, you have only the margins. And then individual post-stratification is done on the margins, each in turn. So first you do post-stratification on gender, then on age, and then on education. And then you do again, because then the fit for gender isn't perfect anymore, and then you start again with age, and then gender, and then the education. And you do that a number of times until the weights don't change anymore, and then the things converge, and that's raking. So, and post-stratification, this is done in one step. Okay, both post-stratification and raking are special cases of calibration. So that's why I often talk about calibration weights, and they can be constructed using a post-stratification or a raking procedure or a generalized linear calibration. But that's like the overarching term that I'm using is calibration weights. Okay, so post-stratification weights are provided by the ESS. The weights are constructed in such a way that they replicate the cross-classification of these three variables: gender, age, and education, and a NUTS2 region classification. So this regional classification NUTS from Eurostat. So it's done on the cross-validation of these three, and then on region. Okay, I will skip that because this is just data processing. If you want to repeat that, you can use that code to do this. It's not necessary here for the presentation. So now I'm using the R survey package to define the sampling design or the survey design of Austria in ESS Wave 8. Here I'm having to use this option survey lonely PSUs just because I'm having so-called lonely PSUs within strata. So the sampling design uses stratification. So the selection of PSUs is stratified. Maybe due to non-response and so on, there are only one observation from one PSU in a stratum. And that can happen. You select like two PSUs, and one PSU nobody responds, and the other one just one element responds, and then you're left with one observation from one PSU from one stratum. If you look at the variance estimation formula for certification, you see that you need at least two observations per stratum to do variance estimation. With only one unit in one stratum, I cannot do variance if I have only one observation. So at least technically I need two. Better to have more, of course. So this is just a way of adjusting that. I think I have to see what it is, but I think it takes the mean variance. So in other strata, it's possible to calculate it within strata variance, and so just the mean value of that is, I think, used here as a stand-in for this stratas where you cannot calculate it within strata variance. So that is one thing that is being done here. Then I'm defining the sampling design. So I'm having multiple sampling stages. But, first one, PSU, that's actually the name of the variable in the data set. That defines the primary sampling unit membership. It's called PSU. Then second is just the indicator variable for each element in the sample. So the identification number. Then strata. So I called that. I gave it the name here. It's called stratify, and that defines the stratification of the PSUs. If I would have also had stratification at a second sampling stage, I could also define stratification within PSUs. Maybe that's not often done, but it's possible. So with this formula logic here in the survey package, you can define multi-stage sampling, and you always define sampling unit stratification, and FPC is not available also, but also final population correction for each sampling stage. So if I had a second sampling stage where also stratification was used, I would then have here a variable that defines the stratification within PSUs. Okay, so I'm using here the weights provided by the ESS, the post-certification weights. I rearranged them a little bit because the ESS, scales them and I rescaled them, so that's why there's this annotation P here. And then I'm defining how these post-certification weights have been constructed. So this is the cross-classification of gender, age, and education, and that is region. But this is the calibration formula. These are the two variables, so to say, on which calibration has been done. This is simply the data set. Nest is true because for some reason there is PSUs that cut across strata. It's also not nice. Usually, there cannot be a PSU that if you haven't stratified sampling of the PSUs, there cannot be one PSU that isn't two strata. But I think that's the case here. Maybe there's a coding error. So I'm forcing here with Nest that he ignores that basically and it treats, whatever. He rewrites the PSU indicator so that it is unique within strata. Okay, that's it. So that's all I need. So I defined here the sampling design. I'm assigning here this object. This stores now the weight information, how the weights have been constructed, and the available design information that I have from the ESS. So this is the best I can do at this point. And now I'm just estimating the mean of this variable trust in politicians. I also recoded that in the code before. And this is simply the means, and that's how the output looks like from the survey package. So we have the point estimates. So because that is a category variable, he will estimate proportions of these categories. So I recoded that to have 3 categories. And the survey package will give you a standard error estimate for each of these categories. You can further use that in conjunction with other estimation functions in the survey package. You can also construct functions of estimators and then try to estimate the variance of that. And so on. Having that on the slides here. And that is just another example for this other variable, how satisfied with the present state of the economy in the country people are. Okay, so that's now here again the estimation that I'm doing, with the best information possible to me. This is also just an example. The survey package provides multiple estimation functions and also statistical tests that are being adapted to handle complex sampling designs and also, of course, the weights. So this is simply a t-test if there is a difference in the proportions between these two, that being low and that being high. And obviously there is, so that's the null of it is rejected here. But the standard error of that test, are being estimated, or standard error that is needed for the test, are being estimated by considering the complex sampling design and the weights, and in particular, how the weights have been constructed. Okay, so what would happen if I would ignore all that and say, simply use the weights? So I know I have to use weights, and that's all I'm doing here. I'm defining the weights. So I'm not defining strata, just defining the IDs and so on. And this is just one. It's basically like a similar example, but I'm saying, use these survey weights. Okay, now this is just a comparison. On top, you see the point estimates. You see they don't change at all. Obviously, I'm using the same weight. Point estimates won't change. But the standard error estimates, they will change. And you see here, W is with the weights and the survey information, and N stands for naive. So I'm only using the weights here. And including the information on how the weights have been constructed, and in particular that I'm having here this multi-stage sampling design with PSUs that tends to lead to higher standard error estimates, then I'm ignoring that. So here I'm overconfident with my results because I'm ignoring the complex sampling structure. But again, the point estimates are the same. So problems also usually just show in the standard error estimation. Okay, just to illustrate the effect, of telling the survey object how the weights have been constructed, I'm estimating here with this naive approach where I'm only, using the weights, what the distribution of region is. Remember, the weights have been constructed to replicate this distribution. But, because that survey design object doesn't know that, I'm getting here standard errors associated with these estimates for the proportions of these different regions. If I'm using the survey design object where that has been defined, that is correctly 0. Because the survey object knows the weights have been calibrated to replicate this distribution, so there is a 0 variance on that. It will always, regardless of what sample I have, or what set of respondents, I'm calibrating the weights of that sample to replicate this distribution, so that it will be invariant. So there's a 0 variance here, and it's then correctly shown if I'm defining the survey weights. Okay, this is just another example of what you can do with the survey package. That's just a table. Here the joint distribution, and then I can do also test of association. I'm using here the statistic F statistic with the Rouse-Scott adjustment. That's the default, and this is also specially adjusted statistic to use the correct number of degrees of freedom that are associated with your complex sampling design. So again, we see that these things are not independent of each other. One more example is using a survey GLM. This is generalized linear regression, which is also implemented in the survey package. Here, I'm constructing here this binary variable, if this takes on the value of 1 or not. And I'm using here also data from the ESS on voting behavior to model this variable. And that's then here being done with this survey design object where I'm defining the design and the weights correctly. So, and just as a comparison to, again, to where I don't do that, you see estimates of the coefficients, they don't change. It's the same thing, but the standard errors change. And that's the main difference, or the only difference that you would see here. Okay. So, do we have time for a longer example?
We have another 35 minutes in total.
Okay. Okay, so what we covered now is just a brief introduction on how you could define, or set up your estimation under a complex sampling design, and if you're using survey weights, and showing you how what different survey weights there are, and in general how they are constructed and what purpose do they serve. What I'm doing now here in this example is to show how variance estimation can be done, where you consider the process of response, which introduces variance, because it is assumed to be this random process where every unit has a probability of responding. So sometimes it might respond, sometimes it won't respond with a certain probability. And then the uncertainty associated with estimating set response propensities, because again, this is only an estimate, and you will have an error associated with your estimated features. And that's all not included in what I just showed. There, I defined how the calibration or the post-certification are being constructed, but I didn't incorporate any, the variation that is introduced into your estimator by the random response process. Would have been hard to do here because I only have the net sample. And the estimate response propensities, I need a gross sample. And that's what I'm doing here in this example. I'm using data that is available in the survey package. It's the data set is called API. That is data on some Californian schools in California. And I constructed there some non-response. So I draw a sample and I construct non-response process. So I'm showing you how you can use resampling to incorporate all factors of variation that there are into your standard error estimation. So this is this the first three-step procedure. So first, we resample the growth sample. So we have our growth sample that's been selected and went into the field. And that's being resampled. So then we have a reshuffle of that growth sample. And then we estimate the response propensity of that resample. Again, then this is like then a random composition based on the resample, or if I'm using a bootstrap, will be a random composition of respondents. Because the number of respondents, will be random if I'm using a bootstrap to resample the growth sample, depending on which elements I'm resampling from the growth sample. So I'm estimating the response propensities for the resample, and then I'm calibrating on the product of the design weights multiplied by the estimated response propensity to resample. So I'm repeating the process of estimating response propensities and calibration. And then here, I'm doing it in a bootstrap procedure. I'm repeating step 1, 2, and 3 many times. And then I'm getting a set of so-called replication weights or replicates of my estimator. And over these replications, I'm estimating standard errors. And if that procedure here, with this resampling of the growth sample, I'm introducing the variance that is due to the response process into the procedure. Here, I'm covering the variance that is due to the estimation of the response propensities. And here, I'm considering the effect of calibration. Okay, so that's what I use for that example is the two-stage sampling designs with stratification at the first sampling stage. In the data set, in the example that I compiled, the stratum sizes are known, which was not the case in the ESS. The ESS doesn't provide the stratum sizes. So I can use finite population correction to actually use the proper variance estimator for sampling without replacement. And PSU sizes are known. So I can also define the PSU sizes. So here, districts are sampled and then schools within districts. So these are the two sampling stages. And then schools, respond or they don't respond. And for the non-respondents, only a limited set of information is available that I can use for response propensity estimation, which is school type and this academic performance index from the year 1999. So, okay. Now, I'm doing that one time without the replication. So I'm defining here my survey design object. This is the ID number for the districts. This is the ID number for the schools. These are the strata for the districts. These are the stratum sizes of the strata districts. And these are the sizes of the districts. So, number of districts within strata, number of schools within district. Name of data. Now I'm estimating response propensity. I'm using survey GLM and using here the data from the growth sample. What the survey package does here, you see, I don't define here any weight. But because I'm providing the finite population correction, it will compute the appropriate design weights. Because the survey object knows how many elements are there in the sample from each stratum, so how many PSUs are there from each stratum, and it knows the size of the PSU. Everything else besides, it assumes that it is a simple random sampling with stratification at the first sampling stage. So districts are sampled from strata by simple random sampling without replacement. So the information is there to compute the inclusion probabilities and therefore the design weights. of the first sampling stage, and the same is true for the second sampling stage. I know how large the districts are and how many schools are sampled from each district. So the inclusion probability of the second sampling stage, conditional on the first one, is also there. I can construct the inclusion probabilities for each school under this design. And it's automatically being done here. So I don't need to define explicitly sampling design if I'm saying, that's the size of strata and PSUs. Okay, so thing to note here, I'm not just estimating response propensities with a GLM, I'm using a weighted GLM. Because I would like to make inference on the population process of the response. That's why I'm using here a weighted regression, and not just a simple regression on the growth sample. Then this is just some R code for adding the information about the estimated response propensities here. So theta x being estimated, so that's the estimation function. This predict is just to get the predicted values on the response scale out of that function, so that I have here my features, and here I'm just adding this information to the data set. That's here, that's my new weight PW. That's the inclusion probability times the estimated response propensity. So in the inverse of that, that's my new probability weight. So, and then I'm constructing here my net sample, and then I can define the net sample. And with the net sample, I'm using now the weights argument, because I have these survey weights now where the design weights are adjusted by my estimated response propensities. Last step here is the calibration. Now I'm calculating calibration weights using the survey package. The population data is stored in this data set APPOP. That's how it's called here. That comes with the survey package, and you can load that if you've already loaded the survey package with data API. And I want to calibrate on the total of this academic performance index in the year 1999, and then on school type. So types of school, this is elementary school, middle school, high school. So these are the population totals that my replication weights should replicate. So replication function works the following way. You hand it a survey design object, which stores the information on the sampling design and the sampling data, survey data. Then you define, how on which variables the calibration should run. Here, this is my cal fm, the calibration formula. And then, of course, I have to supply the population totals that should be replicated, which is here pop mark. And I'm simply calculating this here using the model matrix function. You can look how this works, but this is just, computes the totals for these variables out of that data set. And then you can also specify here cal function. I'm using here the ranking algorithm. I could also use linear. I think log is also included. So calibrate will now compute the calibration weights. If you maybe do that in practice, then it could always be that this doesn't run through. So that this throws an error at you. It tells you, calibration didn't converge. Of course, if I would add here many, many more variables, the calibration problem becomes complexer and more complex. So it becomes more difficult to find a vector that satisfies these conditions. So maybe then you have to cut back or to aggregate some categories so that the calibration runs through. Or you could live that the calibration won't be perfect. There's an option in the calibrate function where you can set the so-called epsilon, which cuts, the calibrations on slack. So it's it doesn't require any perfect fit, but you can say I'm tolerating like a 2%, 5%, variation, so that the totals that are being then estimated with these calibration weights don't replicate your exact population margins, but something that is, has a relative difference of 5%. Calibrate also gives you the option of setting bounds. So often is, maybe you venturing outside pure design-based inference, and you would like to do model-based estimation. the weighted maximum likelihood, and there it's undesirable to have a huge spread in your weights. You can try to restrict the spread of the weights in the calibrate function by using the bounds argument. And you can set a lower and an upper bound. And calibrate then tries to satisfy these calibration conditions, to replicate these known population totals or population values, while at the same time having no weight that is lower than your absolute lower bound and your absolute upper bound. This, of course, restricts the solution space for this optimization problem. And then you can also say, well, with these bounds, I don't find a solution. And then you might have to increase the bounds or increase, the slack, the epsilon, which you are willing to give for that to run through. That is a way of incorporating bounds in your weighting procedure and your calibrating procedure right away. The other way is just to trim it. It might accomplish the same thing by trimming. I mean, you cut, for instance, at a certain value your weights, and then you redistribute the mass basically that's being cut to other values proportionally, so that in sum, again, you come to the population size. Okay, yeah, that's just some side information to the calibration function. So you have the option to set bounds here if you want to try to restrict, the range of your weights. Okay, so and that's then the estimation of my model that I'm interested in. I'm interested in modeling this API, this academic performance index in the year 2000 with the various mobility. Don't really recall what that was. This is a percentage of full-time employed teachers, and this is like the school-wide academic performance targets met, yes or no. Okay, so yeah, that's how the output in Ireland then looks like. Okay, so but these standard errors do not consider the response process nor the variances being introduced by estimating response propensities. They are correct with respect to the calibration. They here you see I didn't define the as I did before in the ESS data where I used the calibrate formula argument to define how the weights have been constructed. I'm using here the calibrate function, and so that object obviously knows how the weights have been constructed because it has that function has been used to compute the weights. So that information is already stored in here, but the correct standard error estimations will be done. Okay, so how can I implement what was on that slide before, where I showed like on the text these steps of incorporating the variance that is due to response to the response process and estimation of response propensities. What I'm doing here, I'm writing an estimation function that repeats these steps, or repeats the steps of estimating the response propensities and the calibration. So first, input is a vector of replication weights. That's the first thing I'm doing. I'm resampling the growth sample, and then I'm redoing for each resample response propensity estimation and calibration. So I'm having here a set of replication weights. Here's I'm redefining a survey design object because I'm not interested here in the standard error estimates that's obtained from that. I'm only interested in the point estimate because, again, variance estimation will be done over the replication of the point estimates. So no need to define any survey information here. I'm only defining here the weights, and that's fine. So, and then I'm re-estimating the response propensities. This is just our code to adding the response propensities or the new probability weight that adjusts the replication weights by the estimated response propensities. That's my new probability weight. It's incoming replication weight from here, adjusted by the estimated response propensity. So then I'm having a new survey design object, PV, are now the replication weights adjusted by the estimated response propensities. And here, this line calibration starts, as you've seen before. Now I'm using that survey design object, and I'm going to calibrate it on the same information as before. And then I'm estimating my regression that I'm interested in. Okay. I'm setting here a seed just to make the stuff reproducible, because I'm using the bootstrap method. This is rescaling bootstrap for multi-stage sampling. I mean, a two-stage sampling here. There are other types implemented in the survey package. You can, there's also jackknife methods implemented. There's a balanced repeated replication that is particularly suitable for certified samples. But I think in this package it only works with 2 elements per stratum. That's a bit annoying. And then there are different bootstrap methods. And I'm using here this rescaling bootstrap. And with 100 replications. So 100 resamples are even done. So it's does, I think, not resample the complete sample size. So it's sampling with replacement, but I think this is not to the original sample size, but something lower. Okay. Yeah, that is the function I'm using here to produce the survey replication weights. As survey rep design is also a function from the survey package. You can compute replication weights for existing survey design objects with the survey package. That's also quite neat that you can do in the survey package. Okay, so but this step does the resampling of the gross sample. Then I'm trapping a survey design object with replication weights, which is a survey rep design. I'm providing the data, type of resampling, bootstrap, where I can find replication weights. These are stored here in this object. So I'm calling here upon them. Combined folds means these are the like the raw replication weights. It's only show how often that unit has been included in the bootstrapping. 1 time, 2 times, 3 times, and so on. And then survey rep will compute the actual replication weights by combining that with the incoming design weights. And design weights being here the weights from the gross sample. Okay, so everything is then prepared. I've written this function that does the re-estimation of the response propensities, that does the recalibration, and I'm having resampled my gross sample. So I'm now doing this replication for each resample of the gross sample, and that's done here with this function with replicates. It's here, this survey design object with replication weights is then added here. And this is just here for the estimation and my output. So here, on what function I'm calling here, that's my self-defined function from above, calest. So these are then my parameter estimates over the replications. And these are my standard errors that I'm having for my coefficients. And if we go back, they are a bit different. First, from here, where I'm only where I'm disregarding the variance that is due to response and response propensity estimation. Most of them are higher. I think that one is a bit lower. Okay, so but this is example, mind you. This is mainly to show or to give you a sense, how you could estimate standard errors that incorporate all the features of variations that you have. Your random sampling, your random response process, uncertainty due to estimation of response propensities, and the effect of calibration. And doing that with resampling is a sometimes simpler way than doing that with a direct estimation or linearization approach. because coming up with an estimator that incorporates, for instance, the variation that is due to the estimation of the response propensities could be quite complex. But this doesn't matter here, because for this kind of applications, resampling is quite suitable, because I can then approximate the variation or really complex statistics by just repeating the estimation process. Okay, so this already is the end of the example, so I'm coming to summary and remarks. So what have you seen? So if you analyze a net sample without considering the sampling design and non-response, just analyzing the data without weights and any design information, you risk not only to have biased estimates, but also wrong standard errors, and therefore also wrong test decisions. And this also applies to measures of association. So not only for so-called descriptive statistics, like totals, means, and so on, where like I want to do some bar plots and so on, and I say, well, for that, obviously, I would need weights. But here, I want to run some regressions, and there I don't need any weights. So we've seen that. I hope I make that clear with the example on the regression, where we saw that the regression lines can obviously shift depending on the response process. Just using survey weights just doesn't take care of the sampling design. So it goes a little beyond that, using weights and in analyzing data. You also, if your sampling design has been complex, you should try to define that somewhere, given the software that you're using. Here I'm using R. In Starter, you can use the survey set command, I think it's called, where you define your sampling design. Otherwise, again, you might have correct point estimates, as you see sometimes in the examples where I'm only using the weights, but I don't define a sampling design. Point estimates are not the same, but standard error estimates are different, possibly wrong. Then weights, especially calibration weights, do not necessarily increase standard error. So there's not a strict trade-off between bias and variance if you're using weights. But that the possible positive effect of calibration shows, of course, you need to have the appropriate variance estimator. So you need to define your calibration weights, and that can be done in R, that can be done in Starter. But otherwise, if you don't define them, the program will assume that these weights are constants, and it will treat them as any other variable, basically in the data set like a measurement. It's not clear how they've been constructed. So simple estimates, standard error estimates, will be used for the computation of the statistics. The weights will be used, but the association between weights and variable of interest won't be considered in your estimation if you don't define or you're not able to define the calibration weights. So also, you should worry about standard estimation as much as you worry about your substantial parameter estimates, maybe even more, because that's usually the tricky part. As we've seen, getting to the correct point estimates, so apply the weights, you're there, but having the correct standard estimates it's more tricky and much harder. Then, maybe most importantly, get familiar, with your preferred software to handle complex survey designs and survey weights. If you are a user and you not already know about a survey package, you can check out a survey package. There's already like a little cosmos built around that, maybe because this has been around for so long. You've seen the first book was published over 20 years ago. There are many other packages that incorporate the survey design or are being made to work in conjunction with the survey package. And in Stater, you can use survey cal to compute survey weights, and also survey set in Starter to define your sampling design and define your calibration weights. That's also possible in Stater. There you have to tell what is the calibration function, just as I did in R, and what are the population totals on which has been calibrated to. Yeah. Then, to do that, learn if you analyzing survey data with weights, learn how these survey weights have been constructed. And then, particularly if these are calibration weights or rate or called post-stratification weights or rating weights, that's the method by which they have been constructed. Which variables have been used in here, so to which variables are they calibrated to, and supply that information to your estimation routine. Using survey weights for non-probability samples is similar to the framework under estimation under survey non-response, but the assumptions, are maybe even harder to justify. As I said, this framework that we have, response is independent of each unit. Every unit has a certain probability of responding and so on. So I can basically model that like Poisson sampling. Making that assumption about probability samples maybe a little bit far-fetched in most applications, that I'm simply saying, well, I have this target population, then I have this a lot of data that has been gathered somehow, and I'm saying, well, it's Poisson sample. Yeah. So the methods are similar. If you're going into the literature of non-probability samples, it looks similar to what you see under treating on a non-response. Simple weighting methods are just calibration weights. You have your non-probability sample, because every unit has a weight of 1 starting weight. Then you calibrate to some known population statistic, which you think, from which your data has been collected, which you get from official statistics, and that's it. And then you have these simple calibration weights. And obviously they work if these variables were suitable to explain the participation in the non-probability sample. But yeah, it's questionable, and you usually cannot test that, and so it's a hard assumption. There are certain limits to using survey weights, because basically this is also the limits of design-based inference. If you're using model-based methods, in particular those that make explicit distribution assumptions, those methods usually have not been made with survey weights in mind, or they come from a different framework. Come from the model-based world where we deal in distributions. These distributions, describe infinite populations at the normal distribution. Normal distribution is an infinite, every theoretical distribution is an infinite distribution, and here we have empirical distributions. That's a finite set of elements. So this is a bit of two different worlds, and sometimes they are hard to reconcile. Also in Bayesian, if you're applying Bayesian methods, often maybe you can use weights and then they are treated as frequency weights, but it's not exactly what survey weights are. So yeah, there are difficulties, or there might be some ways, to instead of weights, you could try to model the data generating process in your model if you want to stay completely model based. But then you might end up, having a bunch of variables in your data that you only have in your model, that you only included because you have to model the data generating process. And then you have to integrate them out again of your model if you're only interested in the substantive variables. So it's that is certainly kind of a conflict and sources of headaches. If you want to use estimation methods that don't really were not really made for to work with survey weights.
Stefan, we have only 5 minutes left.
I'm done.
So yeah, I was wondering whether we should use this
For discussion.
Yeah, for questions from the audience here, from the small audience here, but from the much larger audience online. Thank you very much for this great presentation. And there's already a first question. Alex, if you want, unmute yourself and just ask Stefan.
Yeah, sure. So, can you hear me?
Yes.
Okay, so I assume this kind of goes in the similar direction as your last point about limitations, but especially since you mentioned the ESS as an example, of course, the ESS is a cross-national survey, and something that I've encountered before, a problem that I've encountered before when analyzing ESS data is I want to do a cross-national analysis and say I have an effect on the country level. So I need a mixed model. I need random effects to be able to model that. I have not been able to find a way to reconcile those things. So to have both some sort of estimator for the standard errors that takes the survey designs into account, and also be able to have random effects in the model. Do you know how that would be possible, or is that just something, one of those cases where it's not made with survey rates in mind, as you put it on the slides?
Yeah, I mean, it depends if you're interested in country effects. How many countries do you consider? So it's maybe it's not necessary to have a random effect in there. So the samples in the ESS, I mean, you can see the countries as strata, so the samples have been selected independently within each country. So you could do estimation independently within each country. And you wouldn't lose any efficiency there if you're interested in country-specific differences. So yeah, well, so maybe you don't need a multi-level model to look at country-specific effects. The other thing is, I mean, if you Google, you can find many things. I mean, I think I've come across some adaptation for design-based estimation with a multi-level model. But it's some time ago. I think I would have to check again. But yeah, maybe there is a way of avoiding using a multi-level model of that if you don't have that many countries in there. I don't know how many countries you're considering.
So I mean, for the ESS sample, the ESS usually covers about 30. So that would be an example.
Yeah, and it's necessary for you to have them all in one model because you want to have also effects that like are across all countries. Like you have coefficients, that they run across the countries.
Yeah, I mean, basically that's part of why the ESS exists, is to like measure Europe-wide trends. And then you would want to have that across as many countries as possible. But if, say, you want to consider in modeling that some things that vary by country and might have an effect on things that vary on the individual level, that's kind of the use case that I was thinking of.
Yeah, I mean, yeah, I mean, of course, I mean, you could try using a dummy for the country. It's yeah. Out of the top of my head, I don't know any. That is one of the things like a multi-level model that works well with survey weights. Yeah. No, I would have to think about that. But yeah, usually the way I try to avoid that, if I don't really need the random effect, I try to work then with dummies if it's not too many.
All right. Are there more questions from the online audience or on-site audience? I mean, we're at the end of our time, but I do want to, if nobody else has a question, I do want to ask something. So what I observe also in teaching is that design and analysis of complex survey data is seldom part of typical social science curricula. And I mean, this is probably a little bit more than typical users of survey data use when they get some survey data, they just analyze the data. Maybe like they throw in some controls and they read that as long as you throw in the controls that would go into the weights into your regression model, you're fine. They like dig up some reference and then that's it. Can you tell us something like from your point of view, where are we going with this? like, what should we do? Do we need to include more complex survey design classes into our curricula? I see this as part of, say, GESE's trainings at summer schools, but my hunch is a lot of researchers in the social sciences do not really care about this. A bit provocative, maybe.
Yeah, I think it's you can find many courses on that. I mean, in GESE Summer School is regularly there, and I also once gave GESE Summer course in this. They are frequently visited, so they were they're still quite popular. Yeah, I think it makes sense that you how to say that you get at least an understanding of this concept of design-based inference, how that works. So where for instance, where it's come from and what purpose do they serve. So to avoid that you are in this situation where in this murky territory, where you have this. I think I'm interested in models, and so I'm thinking about causalities and so on. Then I don't use weights and this stuff like that. So I think it would already go a long way if you would, how to call it, if you were able to get rid of these opinions or superstition, how you want to call it, that surrounds the topics of survey weights, where you're still around, you see these best practices, and you do it once with weights, you do it once without weights, and then if nothing changes much, don't use the weights. And I don't think it takes much to make people understand how this works. So I don't think that you need like a dedicated course in your empirical education in social science or your quantitative education that is dedicated to analyzing complex survey data. If it's part of your statistical education, like a module or two, so that you understand the concept, because if you know how that basically works, and what the weights do, how they're being constructed, and the statistic is already there now. The software statistics is there. You only need to know how to use it, and this can be self-taught. If I have to say the survey package in R is a bit awkward and clunky, like at first, how you use it, like so it takes certain time to get used to it, especially being fluent in it, let's say. But you can self-study this and work with examples and so on. So I don't think that like mandatory dedicated courses to that are necessary. It would be over the top because some people don't want to do self-statistics research. That goes too far. But if you have a basic understanding of that, and then okay, if I'm analyzing the data, I'm looking into what offers my preferred software package, what's there, and then you only need to know how to use it.
All right. If there are no more questions, then thank you once again. This was a great presentation. Our next event in the Social Science Data Lab, we will be back on May 21st with a talk by Hanna Reisky and Cornelius Erfurt, Hanna from the University of Mannheim and Cornelius from Witten-Herdecke University, who will be talking about predicting the 2025 German federal election. Thank you very much for joining us today, and see you next time.